Let's start with some definitions. First of all, what is an antiderivative? An antiderivative is a function of a given function. So if I say capital F is an antiderivative of another function, little f of x, then that means when you differentiate the capital F, you can write it as ddx f of x equals f prime of x, okay? The derivative of capital F is equal to little f. And you've seen examples in your Calc 1 and 2. So for example, I know the derivative of x cubed is equal to 3x squared. Therefore, I can say the function x cubed is an antiderivative of the function 3x squared. Okay? All right. So that's one definition. But this is a little lengthy to say, oh, this function is an antiderivative of another function. So therefore, we have another definition called indefinite integral. Okay, so now this is saying, okay, if I use this notation, very slim long s f of x. When I use this notation, then it returns all antiderivatives of this function, little f of x. And this little f of x has a name. It's called integrand. Okay? All right. So if we again use this example, 3x squared. Okay? So from what we just observed, we know that x cubed is one antiderivative of the function 3x squared, right? But if we add any constant, because the derivative of a constant is always equal to 0, we know that x cubed plus any constant is an antiderivative of 3x squared. All right? So this is all antiderivatives of 3x squared. Okay? All right. So with that being said, we can then come up with a bunch of integral formulas. When I say a bunch, it's really not that much. It's about 6. Okay? And they're coming from derivative formulas. So basically, it's like, you know about all the derivative formulas, and now you write the reverse formulas and you call them integral formulas. All right, so let's start with power functions when you have x to the n. Okay, now I want n being any number except -1. Okay, so when you have a power function, then antiderivative will be you raise 1 power and then fix the coefficient, all right, and then plus c. Okay, so now notice that if you differentiate 1 over n plus 1, x to the power n plus 1 plus c, this gives you that, right? Okay, and then n plus 1 and n plus 1, they cancel, so you do end up a single x to the power n. All right, so that's what I mean that integral formulas are reverse formulas from derivative formulas. All right, but you just got to memorize them all. Second, if you have c, a constant, all right, so this will give you c antiderivative 1. Okay, so now notice that this is a special case from the first formula. So this is the case when n is equal to 0, right? Because x to the power 0 is equal to 1. Okay, so then this is a c. All right, so then x, you don't have to apply the formula from the first formula. You can just know that derivative of x is equal to 1, therefore antiderivative of 1 is equal to x. Okay, so either way works. And then plus any constant. So to distinguish, I have two different constants. One, I use the little c from the original integral, and then I use capital C for any arbitrary functions, any arbitrary constant. All right, so this is a special case from the first formula. And then we have trig functions, sine of x, so that will give us negative cosine x plus c. Why? Because the derivative of cosine is equal to minus sine. Okay, so this minus sign here is to fix the minus sign from the derivative formula. And then antiderivative cosine is equal to sine x plus c. And then we have the exponential function, because we know derivative exponential is equal to itself, so surely antiderivative exponential function is equal to exponential function itself. All right, last, this is when n is equal to -1. Okay, so this is 1 over x. All right, so antiderivative 1 over x is equal to ln x. Now keep in mind that it's not just the ln x, it's ln absolute value of x. Okay, and then plus c. All right, so these are the 6 formulas that you should memorize for our class.